So this is, before we start with the naive-based classifier, there are few probability concepts that you should be aware of. The first one of them is that what do we find the probability of? We find the probability of an event. We find the probability of an event, and that event can be independent and that event can be dependent. Now, when we talk of independent events, when you flip a fair coin, so flipping a fair coin, it is going to give you a probability, it is going to come out heads or is it going to come out tails? And when you flip it the second time, would it depend on the first flip? No, right? So yes, it won't. So these two flipping, when you flip a coin twice or thrice, each flip is an independent event. Then there are dependent events, like you have a deck of cards. You take out one card and it comes out to be, let's say, Jack of Trades. Oh, sorry. Some card, some Jack, Jack of Hearts. Then when you take out the second card from the deck without replacement, without putting that Jack of Hearts in the deck, is the second event dependent on the first event or independent?
It is independent only.
No, it is not independent. When you have, when you draw out a card from the deck.
Oh, draw out the card. Okay, okay. I thought you were putting a card. You are putting it. Okay. Like a coin only. Okay.
No. We are drawing a card and without replacement. Drawing two cards without replacement, one by one from a deck. So this is an example of dependent events. Okay. Now,
but how you are saying that this is a dependent? Is it because
okay, I'll try to explain in the paint. What we have earlier is that first time we have 52 cards, right? So probability of getting any Jack of Hearts is 1 by 52 because it's only one. Now when we try to draw second card, you can immediately recognize that there are 51 cards. So the deck has changed. So the deck at the time of second draw has changed because we are doing it without replacement, right? So it's an example of dependent events.
Oh, okay. Yeah, you can just tell me. You don't need to type also.
Yeah. Now addition rule. Addition rule is that PA or B equals to PA plus PB minus PA intersection B. This is called AND operator also, and you can visualize it in the using a Venn diagram also over here. Is there any confusion in the addition rule?
No. It is fine.
Then multiplication rule. PA intersection B equals to PA dot PB given A equals to PB dot PA given B. Is there any confusion in this? It is like you have to, when this forms the basis of Bayes' theorem later on, but when you find the intersection of A and B, you multiply A, and when they are dependent events, if they are independent events, PA intersection B is equals to PA multiplied by PB.
That PB by A means PA multiplied by PB by A. B by A means
no,
what?
it's not B by A, it's B probability of B given A, that you have already been given that
Okay.
event A has happened, and event A has happened, and now you are seeing event B. Okay.
Okay.
Now Bayes' theorem is just a reordering of multiplication rule, where you see that P C given A equals to P A given C multiplied by P event C divided by P A. Are you able to see that this is just a reordering of this equation above?
Yeah. It is just a reordering of yeah. The same means almost similar. It is not exactly similar.
Reordering of the equation. Basically, Bayes' theorem is reordering of the multiplication rule for dependent events. And this Bayes' theorem can also be stated in the form of this posterior because you already A event has already happened, and A is your evidence. P A is evidence. P C given A is posterior, which we are trying to find. P A given C is likelihood, and P C is your prior. These form the basis of Bayes' theorem, what naive Bayes algorithm that we are going to study. Now, what we have to see over
But
here.
here, Bayes theorem. Sorry for interruption. Yeah, the base posterior means it says like a posterior that P for
Evidence has already happened.
evidence.
Evidence has already happened. Then you find the posterior. It's PC given A. Are you getting it?
See.
Posterior is PC given A.
Yeah, I mean C event has already occurred, and we are trying
No,
to.
it's not C, not C. A event has already occurred.
Okay.
Then we are trying to
Okay.
find what
C
is.
given A.
Yeah. This may be a bit
So.
confusing, but it will require me to take a session on probability separately. But these rules are the basic rules of probability. Shall we?
Yeah. Sure.
Now, what is the probability of getting class CK and all the evidences 1 to n? This is a question. Now, what is the naive Bayes condition is that all the evidences and xn are over here in this equation, right? You're seeing CK, x1 till xn. So x1 to xn are our evidence events. You have to memorize this thing. This is kind of a formula.
Okay, this is a formula.
These are formula which you have to memorize by heart. Xi, x1 to xn are your evidence events, and naive Bayes condition is that they are all independent. That means when x1 happens, it has nothing to do with x2, and when x2 happens, it has nothing to do with x1.
It's all other x's,
Yeah, for all other x's, x1 to xn. Now, on the basis of that, we saw that if x1 and xn are independent, we can reorder them ck x1 and xn in the form of this px1 to xn ck. Then because x1 and x2 are independent, we apply the rule of intersection, and where and is x1 to xn all the events happening x1 and all the events x2 to xn and ck. So we say x1 given all other events in the class multiplied by what's given, px1 given something multiplied by p what is given. This is a snapshot taken from Wikipedia. You can read about it. What I'm trying to tell you is that since x1 and x2 to xn are independent, they can be expanded in this form.
Okay. All right. Yeah.
But once we see the example, it should be a bit clear. You memorize this table, not memorize, sorry. This is one of the basic examples. P banana given long, we see that 40. What 40 banana were long and 10 banana were not long. 35 banana are sweet, 15 are not sweet. 45 are yellow, 5 are not yellow, and then total number of banana counts is 50. Orange, 0 are long, 30 are not long. 15 are sweet, 15 are not sweet. Orange, 30 are yellow, and 0 are not yellow. So total number of oranges is 20. And any other fruit, 10 are long, 10 are not long. 15 are sweet, 5 are not sweet. 5 are yellow, 15 are not yellow. Now, when we have to find out that a fruit is long, sweet, and yellow, is it banana, is it orange, or is it different fruit? This is the question. Now, this is one of the basic questions that can be solved using Bayes theorem. So, what do we have to find? We have to find P banana given long, sweet, yellow. If you right, P
Yeah.
long,
Right.
so P banana long and sweet is equal to P long, sweet, yellow given banana divided by probability that it's long, sweet, and yellow. This is through the Bayes theorem, if you remember.
Probability of banana long, then sweet yellow.
Yes.
Okay. And then equals to probability of long, sweet yellow happened in banana.
1 second. Let me also be sure about it. I think
From where you got this problem?
this was from a bits course.
Oh, okay.
So P banana given long, sweet, and yellow. So this is 1 second. PA given B equals to PB given A multiplied by okay, there is one more thing I think I need to write. Okay, there is a mistake over here in this slide, in this page. I'll fix that.
Okay. What is the mistake you're saying? Means it should be
P banana.
first it should be long.
No, P
Long, right?
banana given long, sweet, and yellow equals to P long, sweet, and banana. Then P banana should also be there. Over here, it should be P banana also.
No, divided by P banana it should be, right?
No, not divided, multiplied. P banana should be multiplied over here also.
Why are you saying so?
1 second, because if we use this theorem, right, Bayes theorem, PC given A equals to PA given C multiplied by PC divided by PA. So
okay, PC given A equals to P. Because here there are three parameters. Okay. Long,
yes,
sweet, and yellow, right?
yes.
So P long, sweet, and yellow given banana.
Yeah. So we would have
I mean multiplied by P banana.
Yeah, multiplied by P banana divided by P long, sweet, yellow. This is just one mistake. Then we are expanding this thing over here. P long, sweet, yellow given banana equals to P long, sweet, yellow banana divided by P banana. This is correct. Then naive Bayes, all events such as L, S, B, Y, B are independent. There should not be B over here. But now using the chain rule alongside independence condition, chain rule, the slide I was showing you, This slide I was showing you,
Hmm.
this P long sweet yellow given banana. So we know that long sweet yellow and long sweet and yellow are independent. So as we can see over here, px1 given all other conditions, px2 given the rest, pxn minus 1 pxn comma class, then pxn given class, then pck. So this is what we are doing over here. Since we know that
So this chain rule, where it will be used? Sorry for the interruption. Where exactly this chain rule will be used?
in expanding this thing, expanding
Okay, okay.
expanding this probability.
Mhm. Okay.
Now P banana is 0.5, 50 by 100, P orange is 0.3, P other fruit is 0.2, P long is 0.5.
So this is some assumption value we are assigning
No,
this
this is
banana.
from the table. This is from the table. Total number of long
Okay, okay,
are,
50, 30, 20, 100. Okay, okay.
yeah. P sweet is 65,
Mm-hmm.
P sweet 65.65.
Mm-hmm. And out of 100, okay, okay.
Yeah.
P yellow is 80.
0.8. Now P long given banana, we can refer the table. P long given banana, P long, there are 50 long and number of bananas are 40. So 40 by 50 is 0.8. P long given banana is 0.8. Now over here I have rectified the mistake like we were referring earlier. PB given LSY equals to P LSY given B multiplied by PB divided by P LSY. Right? Now
Correct. P.
Over here we see it again. P banana given long sweet and yellow equals to P long given banana multiplied by P sweet given banana multiplied by P yellow given banana multiplied by P banana divided by P long sweet yellow. So this is the P evidence. What we have in the denominator is the evidence. P evidence
Okay.
comes
That
as
is called as evidence. Okay.
Yeah, and then P long sweet, P long given banana, P sweet given banana. We refer to the table for this. Shall I show you the table for P sweet given banana?
No. I got it. Yes. Whatever the long banana are there, percentage you have just taken percentage. You are long, sweet, and yellow. That factors only out of 100 you have just taken, and then you are dividing it by
Shall
long,
I
sweet, and yellow.
show you P orange given long sweet and yellow is 0?
Okay, that value is also coming from the table only, right?
One second.
Yeah.
So I'll show you that P orange given long sweet and yellow is 0 because we have, if it is given that the fruit is long, if it is given that the fruit is long, then the probability that it is orange is 0 because of this 0 over here. Then P similarly.
Just 1 minute, Ashish. Just
I try to wrap up quickly. Naive-based
yes. Let's quickly
classifier
wrap
is
up.
naive-based classifier is an extension of these ideas only, that we have P, this posterior is equals to likelihood into multiplied by prior divided by evidence. This, based on this only, we will find out if a mail is spam or not spam. So we have two classes, ham and spam. So this is the training data: good, very good, bad, very bad, very bad, comma, very bad. Then if we get the test data that a document is coming into as input is good, bad, very bad. Now what is the probability that it is spam, or what is the probability it is ham? So P ham given
Ham
D6
means does, sorry for
not
interrupting. Okay, not spam only.
Not spam. So P ham given D6 and P spam given D6. D6 is this: P ham given good, bad, very bad equals to good, bad, very bad ham divided by P good, bad, very bad. We are replacing the D6 with the words in the document. So p ham given d6 is this, and then we try to find, then we know that p good, bad, very bad equals to this, equals to this. Now if we go p ham is equals to, what is the probability that it's p ham? Number of documents which are ham divided by total number of documents. What is the probability that a mail is spam? Number of spam mails divided by total number of documents. Then what is the probability that you see the word very given that it's ham? So word term very comes, how many terms are there in ham, and what is the probability that it's very given ham is number of times term very appears in the ham. So divided by all the rest of the terms, number of terms times term very appears, number of times term good appears, number of times term bad appears, because these good, very good constitute ham. So but you might be recognizing that we are adding one over here.
Yes, yeah. Why we are adding that one?
Because in the previous problem, if you see that p banana, p orange given long, sweet and yellow turned out to be 0, because one value was 0. P orange given long is 0. So
Your
p
voice is
orange.
breaking, Ashish.
Okay, is it better? Is it
It is
better?
better now. Yes.
So if we
Yes,
have,
it is better now.
if we see why p orange is p orange given long, sweet, yellow is equal to 0, because of this 0 over here. P orange given long is 0. So if we are given that a fruit is long, we don't need to consider any other condition, because orange is nowhere long. This 0 signifies that. So if one probability is 0, this entire term becomes 0. This entire terms becomes 0.
But here, how we are getting that it is 0? The last we have calculated long, sweet and yellow. Prior to that we have calculated banana long, sweet and yellow, right?
Yeah. So
So
this is
that
the
point.
conclusion we are expanding. If we see that p orange given long, sweet and yellow, if we expand it, it will be p long given orange multiplied by p sweet given orange multiplied by p yellow given
No,
orange.
this part I got it is then 0.252 by denominator. Then after that, how they are concluding the next line that we long sweet.
That we have to use using the formula again. P orange given long, sweet and yellow will be expanded to p long given orange multiplied by p sweet given orange multiplied by p yellow given orange multiplied by p orange. So the first term in the numerator is p long given orange. Now what is the probability that orange is long? If we see over here, it is 0.
Long. Yeah, it is 0 here. Yeah, long. No.
So that makes the entire term 0. So to avoid such
Okay.
things, we use Laplace smoothing. This plus 1 is that Laplace. Now this you see over here. What is the probability that p very given ham? We see that very good and bad are there, but ham in the ham mails bad never appears. So if bad never appears, that will make the term, this term 0. But because of Laplace smoothing,
Yeah, bad never happens with.
but because of Laplace
Correct.
smoothing, it is not 0.
1. Yeah, it is 1. Yes.
It will turn out to be 1, and there will be a slight change in the probabilities, and it is 0.33. Similarly, we conclude p good given ham. Abhijit, should we do the Laplace smoothing? We find out the probabilities for p very good, p very given ham, p good given ham, and p bad given ham. Now similarly we do for the spam. We find the probability p very given spam, p good given spam, p bad given spam. And then probability d6 given ham, p good, bad, very bad ham given its ham is P good, bad, very bad ham equals to P ham, P good ham given ham, P B given ham, P very given ham, P B given ham. So PD6 given ham, find out like this, and PD6 given ham is this, then P ham given D6 equals to PD6 given ham, P ham divided by PD6, and then P ham and P spam, we compare these two values, and then the email is classified as spam.